Oh, hello. Welcome to another Learning Glass session. So today we will look at how to look at this control volume of a flow and see how we can gain some insight on how diffusion pops out and how like this total flow of a fluid, gas or liquid, even a solid, we can apply this conservation of mass to compare the mass coming in and out of a mixture with the relative velocities of its components. So here, let's look at this in one dimension. So here's our three-dimensional control volume, but let's just keep track of things in this x direction here. So here's a box, a control volume, and let's just analyze this x direction here. And so this would be a one-dimensional control volume for a mixture species A, meaning that there's many components of this mixture with many species, we call them. And let's focus on A in a mixture. So control volumes is what we use to keep track of mass coming in and out, energy coming in and out, momentum coming in and out, to establish these governing equations. So in this case, we'll focus on a mixture and mass conservation. So for a mixture, there's many components. We'll focus on A. But when you add all those components together, it makes up this total flow or this total mass. So let's do this balance for both the total mass and the species A and keep track of it in this control volume. So for the total mass, there's going to be some, let's say it's coming in from the left side. So total mass, let's call it m dot, kilojoules per second, kilograms per second. And then we'll also keep track of this individual species and do a mass balance on that as well. Species A mass would be the mass flow rate, kilograms per second, only of A. Then there's going to be some flowing in, some flowing out. So this would be from the left side. This would be from the right side. And so let's balance this out as if it were some coming out from the right side. What we're doing here is keeping track of this per volume. There's some coming in and some coming out. And that's what these simple diagram is here trying to capture. Okay, but in any mass balance, we have to consider that the amount coming in might be different than the amount coming out, and the balance could be positive or negative. So there can be some accumulation, buildup of mass inside this volume, or there can be some depletion of mass inside this volume. So that can be captured with this change in mass over time, total mass. And for the species A, this would be the change in mass of species A over time. So it's accumulation and depletion. And for each individual species, there can be chemical reactions. So let's generalize this to some chemistry that can happen in this volume due to production of species A by a chemical reaction or destruction of species A by chemical reaction, and call that this MA triple dot. And so what's happening is there's some being produced, or it can even be destroyed. So it's happening within this control volume, so it's the mass produced per volume due to chemical reactions. And note that there's a total mass flow coming in or out or being accumulated, but there's no source term due to chemical reactions, because due to chemical reactions, whenever you have a chemical reaction, the total mass has to be conserved. The mass on the left side has to equal the mass on the right side. We're not doing nuclear chemistry. It's only simple exchange of electrons to form new bonds. And that means if you have the total mass, that's going to stay constant. There can be some accumulation or just unbalance due to flow, but there can't be any net mass produced due to chemical reaction. So this term here is actually 0 for the mixture. So to summarize, accumulation, depletion is dm dt for the total mass and dma with time for the species A that we care about. There's more than one species in here, but let's just focus on species A. And then species A, production, destruction, due to chemical reaction. This is the mass rate this is per second, but it's also per volume. So this is this m dot triple prime here of species A. But note here, there's no net produced or depleted or destroyed of the total mass, because total mass conserved in reaction. So even if there is a lot of chemical reactions going on for all these different species, the total mass due to this source is 0. There can be some accumulation or depletion, but that's because of an imbalance of flow. It's not because you can have this destruction of the total mass. Okay, so that's these two terms are accumulation, depletion. This is a chemical source term, or sink term. Okay, so how can we quantify this mass? So there's different ways to do it. In the Terns book, they quantified the mass by a mass flux times an area. Another way to do it is to quantify the concentration or the mass fraction times the velocity. So let's do that here. So the total flow total mass flow, m dot kilograms per second, equals the density of this flow times the total velocity of this flow times the area that it's crossing over. So this would be the flow area. This would be the total mixture velocity, and this would be the mixture density. So this kilograms per second, I'll just show here, kilograms per second equals the kilograms per meter cubed times meters per second times meters squared. So these cancel out here, giving you kilograms per second. And this would be the velocity in the one dimension. We're only doing a one-dimensional analysis here. So this would be some velocity coming in, some velocity coming out. And instead of quantifying this by mass flux, flow per second, we'll tie it to the centimeters per second, this velocity coming in, velocity coming out. Okay, we'll do something similar for the species A mass flow. Species A mass flow, similarly, just for this A species, it will be the density of only this species, and I'll show you what I mean by this. It's actually a concentration. So what I mean by this is that another way to use the mass fraction, by definition, is the mass of A, mass flow rate of A, over the total mass. But if this is the same volume that we're working with, so we can use this, and instead of the density, we can use the total density as well, and the mass fraction of A. So again, this is unitless. So this is kilograms per meter cubed times meters per second times meters squared. So similar to this, with this individual velocity of the species and the mass fraction of that species. So this, we're going to show it more how this pops out of this equation, but as we may remember that when you have a mixture flow, there's always going to be a difference between the bulk flow of the total mixture, but also just this pressure-driven or mechanical flow driven by gravity or driven by pressure gradient. That is one source of this flow, this momentum going in and out. But there's another source due to these collisions on the molecular scale that causes a drift between whatever this net macroscopic velocity is. There's always going to be some difference because of diffusion, this molecular collisions leading to this drift from the total macroscopic velocity. So this is the net velocity, which can have some diffusion in it as well. But where does that diffusion come from? It comes from each individual molecule. And in this case, if we have different components in this mixture, each component has a different size, has a different mass, and that gives rise to different diffusion velocities. This is not the diffusion velocity. This has both the bulk motion that follows with the flow, but it also has its own drift velocity, its own diffusion velocity. So how does that work? Let's first write these conservation equations for both the total flow and the species flow. So we're starting off with the total flow. That's going to have this accumulation and depletion term, change in total mass with time. And that's because there might be chemical reactions, but each reaction doesn't have to involve the total, all species in there. But even if you have all these reactions with all these species, the total mass does not change. the total mass only changes over time if you have an unbalance in the flow coming in and out, not because of chemical reactions for the total mass. Okay, so let's start with the mass conservation of this total mass flow here. So for the total mass, well, there's going to be some accumulation or depletion. That has to balance out any change in mass on the left and the right, and there's no source term. So it is this change in total mass over time equals the mass flow rate from the left minus the mass flow rate from the right. And we can do two things to this. We can use this definition here where we're going to relate the mass flow rate to densities and area and velocity, and do the same thing for these over here as well. So this total mass flow, we're going to use both this and this general relationship between the total density. So we're assuming that here, this total mass coming in, this total change in mass, there's going to be uniformly distributed throughout the same density we can apply. And then that mass depends on this volume times the density of the fluid. Then we're going to use these here from the left okay. So volume for the same area here is the area times delta x that's volume, area times delta x. This delta x times the area across here equals A times the left minus this rho u to the right. Okay, so this area cancels out, and if we take this delta x over here, in the limit as delta x goes to 0, we're going to put the x over here. This is where it's going to pop out the conservation of mass, or I'll do this first. Before we do the limit, do one step before that. So the delta x goes here. This is where the derivative comes from, d rho u dx. And the limit of delta x goes to 0 It's an infinitesimal change, goes from this discrete change to infinitesimal continuous function. That gives us our final result in one dimension. So this is the conservation of total mass in one dimension. This accumulation depletion term is balanced by this net transport of mass in or out, carried by the velocity across these one dimension. And we canceled out this area, so it's really a concentration now. It's no longer the mass exactly, it's kilograms per meters cubed concentration now, or densities, which is another way of saying mass per volume. Okay, so that would be the mass balance for the total flow. Now let's start here with the individual species. So each individual species has this mass coming out, and the total mass, we use this already. Okay. So this would be for total mass. Total mass conservation there. For each species, the main difference here is that you have this source term. This is a mixture. There could be chemistry in here. This one molecule A could be produced or destroyed in a chemical reaction. That's what this is accounting for here. So let's do this mass balance and say that the change in the mass of species A over time, this is kilograms per second, is balanced by the mass flow rate coming in from the right of species A, or left, minus the mass flow rate of species A from the right, plus this source term times the volume in this. This is per volume, and then you need to consider the total volume of this control volume to get the mass produced or destroyed. Okay? So we'll use this and the definition of mass density as well that we used here. Mass density is the volume times the total density so this would equal, going from this term, the total volume times the dA dt, and then converting the volume to area per delta x, change the marker here. Area times delta x, and this so this is meter cubed this is mass per meter cubed per second times the volume, and then use these here. So this would be the density of total mixture times the mass fraction of this component times the velocities of this component times the area from the left minus this similar thing, except it's coming from the right. Plus this source term. Also say, instead of volume, the area times this incremental x. So here we use this definition of, we use the express the mass flow in terms of the velocity and the density, and then we converted the density of this one species, which is another way of saying concentration of one species, because it's kilograms of A per meter cubed, and use this definition of mass fraction to convert the mass of this individual species and relate it to the mass fraction in the mixture and express those in terms of mass densities here. So this is another way of saying concentration. And then this individual species concentration, mass per meter cubed, relative to the total mass per meter cubed, gives you the mass fraction. So that's what we're doing here. Okay, so let's plug those in so we can cancel out the areas. So delta x, this should be A here. This is the mass flow rate of A, and we related that to the mass density of A. And that should be here as well, the mass density of this species A, which represents the concentration in this mixture. So this mixture shares this whole volume with everything else. So this mass within this whole volume of everything else gives you the concentration of just A. And then, as we just discussed, you can relate that to the total density and the mass fractions like this, and then the flow coming in and out is can be related to the velocity like this. So the area is canceled out, and again, we can take this incremental change in the x direction, express that in terms of derivative in this control volume, converting these to a differential form here. So dividing all these by x's, the x cancels out there. Again, in the limit of x goes to 0, delta x goes to 0, you get this differential equation for only species A. Oops. The total density times the mass fraction of A and the velocity of A, and then this source term. So that would be the conservation for species A. in this mixture. There's many species, and if we do this mass balance just for one individual species, we can relate it in terms of its mass fraction and the total density of the mixture and this velocity of this individual species. So because there's collisions on the molecular scale, and those collisions affect these individual species differently because of their size and mass, they have a different response to these molecular collisions. They do follow the flow to some extent, but there's also a component of the velocity that can make it different than these individual flows to some extent. So if we were to convert this back to here, instead of mass fractions, use rho the definition of, the way that we use rho so that means we could also express this in the concentration of, going back to this, we can write this like so. So it's similar for species A, just different units here. And it also looks like you see some comparisons with the total mass. The difference being, of course, this is the change in the concentration of A with time due to imbalance of flow. Has to balance off with this change in transport in and out over in the control volume in some incremental direction, left or right. And then there's some source term due to chemical reactions. But the difference here is that for the total mass of all the species, the total mass is conserved, so there's no chemical reaction source term. Here there is, in the individual species, they can have this source term. But another thing to notice is that we can write this total mass here, if we're saying that this mass density of each species is related to the total mass density of the mixture, what that's saying is that the mass densities, it's like a concentration or mass fraction, all the sum of all the mass fractions has to equal 1. Another way of saying that is if we express the concentrations in terms of mass fractions, they all have to equal 1. But if we express the mass fractions a different way, this way and this way is being mass per meters cubed, and they all share the same volume, this control volume V, then if you add up all of the mass densities of each individual species, add up all the concentrations of each individual species, that has to equal the total mass density of the mixture. And we'll use that here to get some more insights into what's happening in this control volume and the difference between the total mass balance and each individual mass balance. So, note for the concentrations, as we know, the sum of all mass fractions have to equal 1, of course. But similarly, if we have a mixture and we're defining their concentrations in terms of mass per meters cubed, that has to equal the total mass of the whole mixture. Okay, this should be I here of all the components. There's A plus other ones. So we can write this conservation of mass the derivative of the sum of all densities equals that. And then we can either apply that further. We can put that in here. So if we ignore without for no, in a case of no reactions, MI, there's no reaction, so there's no production or destruction. You can say from this comparison of these two that from here you get this result. So by the conservation of mass in a mixture, this mass flux of the total mass flow has to balance out these individual components, the sum of all the individual components. Or another way to say this is the total mass flow is the summation of all these components in terms of mass fraction. So the total mass flow is the weighted average, weighted by mass fraction of all these individual fluxes. So in general, in fact, each of these is different. Why? Because they have different masses, and as we haven't talked about it much yet here, but we know that each individual species in a mixture follows the bulk flow, but it also has its individual component diffusion velocity due to molecular collisions that could even make it go backwards or can make it go a little bit ahead. But each component has a different velocity due to diffusion. So each total velocity of each species is different. And those two, the main two reasons, there are going to be a few different reasons, but the main two in like if we don't have any electric voltage or if we don't have a temperature gradient effects, those all can come into play. But if we're just considering this diffusion flux due to collisions, that is proportional to the concentration. So in general, is So they're all different, and they all have a weighted average that contributes to them. So by the conservation of mass, this has to hold. And that gives rise to this other way to introduce this diffusion behavior. Let's cause if drift is only due to mass diffusion, then we can define this diffusion velocity as the difference between the species velocity and so there can be an electrical field that can pull this thing, the different components due to different sizes. There can be a temperature gradient which affects different sizes and masses. But the most simplest case without those external fields would be collisions on the molecular scale. And those collisions affects every species differently. So the difference, the drift between the total bulk velocity of all the components together and each individual components, we can balance that as to say that has to be the diffusion velocity. Okay. So let's start over here again. This is species A. So what this is saying here is that there can be some wave in one dimension, some velocity of the total flow, but there can be each individual components can vary a little bit. So I'll show that as a diagram on this here. So so within this control volume, let's say at this plane here, this would be the total velocity, but each component is going to have a different drift. You know, let's say this is A, and then this might counteract with B, be a little bit faster, and then even might one, by some fluctuation or something, might have something like this. But in general, these all have to balance out. This is U, U. Depending on their mass fraction, they all have to balance out to this bulk velocity here, or this total flow velocity. And without any electric field, that can happen. Electric field effect, that's electrophoresis, and temperature gradient, thermophoresis. They're not exotic, but they're more deep, more specific, because those are used a lot. Electric field is a useful transport mechanism. Temperature gradient happens in flames and causes this migration in flames. And but the most common that happens everywhere is mass diffusion just by the collisions in a concentration gradient. Okay, so if this is only due to diffusion here, let's apply this. Let's define the fusion flux. Let's call it J dot of species I in the x direction equals, what does this equal? By definition, equals the mass density, so it's a flux, let's apply this to A, of this species. Mass flux of A is the mass diffusion flux of this due to diffusion and relative to the total bulk. So this would be and let's plug that into here. So that means into here, rho A UA equals plug that into here, that would give this form of the species balance. Oh wait, this should be bulk. This A does not belong here. And so if we're saying this is only due to diffusion flux, we know a semi-empirical relationship that Fick found for this mass diffusion flux. If we apply Fick's law for binary mixture, this would be JAX equals negative rho D AB, binary meaning A and B, D rho A dx. Wait. This should be mass fraction. And then we'll interplay this. So this is the diffusion flux, is the difference between the species velocity and the bulk velocity. So for a binary mixture, this pops out. So for binary, this total species balance would be the source terms there too. Okay. So this would be accumulation term. This would be the bulk flow, and this would be diffusion. And this would be source chemical reactions. So this would be the mass balance. But we started off by saying this is in general a multi-component mixture, which is good. And we popped out this Fick's law for a binary mixture, which is easy to understand. It's just one molecule diffusing in the other. So how do you express this for a multi-component mixture? Because you have to consider not only this diffusion in one species, A and B, but if it's a lot of components, it's going to be diffusing in this whole mixture. So how do you account for that? So first thing is that depending on the problem, like for some flame code, for example, the typical flame codes, if they define the fuel and the air and the products, you know, like the minimum species would be fuel plus oxygen plus CO2 plus water. That's 4. And then if you want to get more accurate, you have to keep on adding more and more species, more and more chemical reactions, which adds more molecules. So each species has one balance equation. So each species, there's n equations for this, but okay, that's one thing. B also has one of these, but how do you for the diffusion part, you can, there's different ways to do this, but a simple way to account for this mixture of one component and everything else would be to use a mixture average diffusivity. So the D of A mix average equals 1 minus the mass fraction of A over the sum of, not counting self-diffusion, of the diffusivity. So the binary diffusivity compared to each component weighted by the mole fraction. So, you know, it'll be so for each species, A through K, you would have the mass balance equation, and then the diffusivity in question can be compared to, or like you can have the fact that this is not a binary component, that each species has a drift velocity compared to the bulk velocity. And then the question is, how does this diffusivity, can we apply one diffusivity for one species? This is one way to do it. There's a few other ways. This is not the most accurate one, but you get the idea that that it's not only colliding with one partner, it's colliding with everything in the mixture, and that results in different diffusivities depending on what it's colliding with. This averages out all of those different possible colliders you can have in this mixture. But each partner you have in this mixture also has a balance that, depending on the problem, you might have to keep track of as well. So there's a total mass balance equation, and then each species has this equation. In principle, depends on the problem whether you have to solve it or not. And then you might have some chemistry involved, which we have not even touched upon. So this is how these mass balances work with each of these components in the mixture. And this was only considering this diffusion drifting from the total bulk here. There can be other reasons why that can happen, and especially in flames. And sometimes there's a voltage or something that you can make use of this force that you can separate different components like that. Okay, so thank you. I'll see you guys next time.